Hi everyone, I'm Xiao Yuxia, a lecturer from the University of Southern Queensland, Australia. Today, I will present our paper named Formulating Interference-Aware Data Delivery Strategies in Edge Storage Systems. So, here, the first thing we need to talk about is what edge computing is and why we need it. The edge computing just deploys edge servers at the base stations to provide highly accessible computation resources and storage capacities to the nearby users, like the laptops, smartphones, and smart vehicles. It is an extension of the cloud computing. Since the bandwidth becomes much cheaper than before, pursuing the low latency becomes the main focus in the current generation. Different from the cloud servers, which can be treated with infinite resources, the computing and storage capacities on edge servers are usually very limited. This raises many new issues in the edge computing environment, such as computation offloading, computation scheduling, and resource allocation problems. In addition, many applications just rely on the low latency services provided by edge computing. For example, the real-time strategy navigation, like the smart city deployment, online gaming, AR, VR, and other applications. So we just did a small latency test here, as we can see. Here just the results, including like the edge-to-edge and edge-to-cloud communication. As we can see, as we know, like the latency-sensitive application, like AR, that usually requires very low latency, like less than 20 millisecond latency for that, which, as according to the results we presented here, only the edge-to-edge can fulfill like that. That means if we want to achieve such low latency requirements, we have to have some edge servers nearby to provide the corresponding data or services. Thus, we must have the edge computing to power those to put like the resources for powering those latency sensitive applications. Now let's first have a look about the app vendors, because this work is just to formulate problem and solve those problems from this perspective, from the app vendor's perspective. So the app vendor also can be called like service provider or the content provider, like YouTube, like Nintendo or the Stadium, and many other companies. They play a very important role in the edge computing environment because they're the clients and they pay the money for that. Thus, it is significant to solve the problems from the app vendor's perspective. For those app vendors, there are just like two major concerns from their side. The first one is like the cost, like how much they have to pay for hiring like computation or the storage capacities on the edge servers. And the second one is the benefit what they can get, like how much their services can be improved, like providing their users with low latency and high quality services. So let's have a look about an example and the corresponding challenges in the edge storage systems. So as we can see on the right side, consisting by like for edge servers, and the nearby users can access the data which is stored there, or they can access those data directly from the cloud server. However, there is some challenges that must to be faced in the edge computing environment to be considered, as we list on the left side. The first one here is about the resource constraint. Because existing studies, most of them just assume like the app vendors can hire the storage resources at any edge servers on demand at any time, very similar to the resource hiring in the cloud-based storage systems. However, an edge server usually has very limited storage capacities due to its physical size limits. So app vendors cannot assume there will always be adequate storage resources on the edge servers for hire. In fact, app vendors have to compete for those resources for storing their own data. A practical strategy here is to reserve the storage resources on the edge servers in this system, the edge storage system, in advance based on their budget. The second constraint, or as we said, the challenges here, is about the edge server collaboration. Because the collaboration is the most powerful tool in the edge computing, and the collaboration among edge servers, however, is unfortunately ignored in many existing studies. Because the edge servers, they are between just linked by the high-speed links or the fast wireless communication protocols, the adjacent edge servers can share their resources and transmit data to each other. This is about the edge server's ability to collaborate, and it can reduce the data delivery latency without incurring excessive storage overheads. The last challenge here is about the communication interference. Because many existing studies have focused on the computing or the storage aspects and just ignore or oversimplified the communication aspect in the last mile, as we say, during the data delivery in the edge computing environment. The communication between users and edge servers must be considered because multiple users can access the edge servers for data on the same time via the wireless communication. In this way, the wireless interference occurs, and it might significantly impact their achievable data rates and lower the corresponding quality of the experience of those users. Thus, the interference also should be considered during the data delivery in edge storage systems. After introduce the background of this study, now we will present our major contributions when we investigating the interference-aware data delivery at the network edge problem. So the main contributions are just listed as follows. We can see the first one, we formulate and model the IDD problem as a constraint optimization problem from the app vendor's perspective. And also we also prove that the IDD problem itself is NP-hard, because the NP-hard is very hard to be solved in a short time. We develop a two-phase algorithm named IDDG to formulate IDD strategies to find a near-optimal solution effectively and efficiently. At last, we both theoretically and experimentally evaluate our IDDG's performance to demonstrate its effectiveness and efficiency. Let's have a look about the model here. This one is just a mathematical model of the IDD problem. The details of the notation can be found in the paper. So here we also list the corresponding meanings at the left side. As we can see, the optimization objectives here are two. The first one is to maximize the average data rate that received by all the users, and which can be significantly impacted by the interference according to the user allocation strategies. And the second objective here is to minimize the average data delivery latency of all the users. And the following ones are about the constraint or how to calculate. For example, the first one here, that's the storage capacity constraint. That means the data stored on each edge server cannot over its limit or over the resumed or the reserved spaces on the edge servers by app vendors. The second one is about the actual data rate calculation by each device, because normally for each device there is an upper limit for the data rates that can be received. And the next one is to how calculate the data delivery latency from a user to a data. Like we can see fine here, this one is just try to find the lowest one from either an edge server in this area or from the cloud if that's too far away. And the last one here just to present all the data has been stored on the cloud and the user can retrieve any data from the remote cloud. However, one of the possible results is like the latency could be very high if the user select to retrieve a data from the cloud server. And here, because we know the problem IDDE is NP-hard, it is intractable to find the optimal solution in the large-scale scenarios. Thus, we need to find an effective and efficient approach to find the near-optimal solution. The near-optimal result for that. So we can see that on the right side, the pseudocode of IDDEG is listed. As we can see here, there are two phases. In the first part, we formulate a potential game to find a Nash equilibrium as the strategy for user allocation. In this game, each user can act as a player and submit its allocation decision that produces the highest benefit. A random decision will be selected and updated. Such process will keep going until no decision updates are submitted. At this stage, the user allocation part is finished. In the second part, we employ an approximation algorithm to determine how to deliver requested data to corresponding users. We deploy a relatively direct strategy here. Keep selecting and updating the data delivery decision that produces the highest ratio of latency reduction over used storage spaces until there is no any feasible delivery decision can be selected or no storage constraint we can make by storing a new data into it. At the end of this algorithm, the final strategy consisting of the user allocation and data delivery is formulated. The theoretical results of computation complexity, data rate, and latency are just shown on the left side. And you can also find a very detailed process in the paper to see how prove those results. Now let's start to introduce the experiment part of our paper. So the data used in the experiment is a widely used EUA dataset. In the experiments, we only use the data in the Melbourne CBD area, which contains 126 stations and 816 users. For the experiment settings, we compared our IDDEG approach with other four representative comparison approaches. For example, like the first one, IDDE-IP, which is actually based on the model we presented here, and solved by the IBM Simplex. Since due to the NP hardness of this problem, it always takes a long time to find the exactly optimal solution. In this case, we just identify the searching time for the results by IBM Simplex, set it to 100 seconds. The second approach here is SAA, which is sample average approximation approach with originated from a TPTS 2020 paper. And the next one is CDP, the centralized data placement approach that we can just find that originated from a TWC paper from 2017. And the last one here is about a TPDS 2022 paper, which is called DUPG, the approach. And the parameter settings is just same as we listed on the right side. This one is, we can see there is a full set. We change 4 parameters. The first one is number of edge servers, and from 20 to 50 in steps of 5. And the second one is the number of users, which is from 50 to 350 in steps of 50. The third one is number of data from 2 to 8 in steps of 1. And the last one is the network density from 1 to 3 in steps of 0.4. For each time we change a parameter, we just repeat the experiments for 50 times and report the averaged results. And also, once we look at the experiment results, we select 3 performance metrics here. The first one is average data rate. The second one is average data delivery latency, where those two are same as the objectives of this IDD problem. And the third one is a computation time, which means how long to find a solution or strategy for an IDD problem. So let's have a look about here. Those are just about the experimental results obtained from all the 4 sets of experiments. As we can see, for the average data rate, the red one here is the IDDEG that always have the best performance just among all of those 4 sets, and some of them even with a margin very clearly or obviously compared even to the IDD-IP. And for the latency, we can see IDD-IG always at the bottom in those 4 figures compared to others. Those just show the effectiveness of the proposed approach. And this figure is about the computation time that we used here to represent how long to find the strategy. As we can see, the IDD-IP here always takes the longest time here, like from 100 to 200. As you remember here, we set that the searching time to 100 seconds. However, in IBM CPX, except the searching time, there were also like the turning time, decision, filter time, and many other options. And in this case, we find the time actually needed is always higher than 100 seconds. We can see here, this one, the red one here, is our IDDEG. And we can see most time it's just the second lowest time among all the 5 approaches. The CDP is the lowest, but the result we can find in here is comparatively very bad to the IDDEG. And such time difference between the CDP and IDDEG, they're just like the price of the high effectiveness or the high performance of IDDEG. The last one here is about the future direction, about the edge data delivery problem. We think here the user mobility, data popularity, and the security privacy are very important and urgent points to be investigated in the future. And actually, we already start to look at the user mobility and formulating the following works as well. So thank you very much for the listening. And here is my email address. If you have any questions, please feel free to email me and I'd like to discuss with you.